Hypersonic speed. In aerodynamics, a hypersonic speed is one that exceeds 5 times the speed of sound, often stated as starting at speeds of Mach 5 and above. The precise Mach number at which a craft can be said to be flying at hypersonic speed varies, since individual physical changes in the flow like molecular dissociation and ionization occur at different speeds. These effects collectively become important around Mach 5-10. The hypersonic regime can also be alternatively defined as speeds where specific heat capacity changes with the temperature of a flow as kinetic energy of the moving object is converted into heat. Characteristics of flow. While the definition of hypersonic flow can be quite vague and is generally debatable, especially due to the absence of discontinuity between supersonic and hypersonic flows, a hypersonic flow may be characterized by certain physical phenomena that can no longer be analytically discounted as in supersonic flow. The peculiarity in hypersonic flows are as follows. 1. Shock layer. 2. Aerodynamic heating. 3. Entropy layer. 4. Real gas effects. 5. Low density effects. 6. Independence of aerodynamic coefficients with Mach number. Small shock stand-off distance. As the body's Mach number increases, the density behind a bow shock generated by the body also increases, which corresponds to a decrease in volume behind the shock due to conservation of mass. Consequently, the distance between the bow shock and the body decreases at higher Mach numbers. Entropy layer. As Mach numbers increase, the entropy change across the shock also increases, which results in a strong entropy gradient and highly vertical flow that mixes with the boundary layer. Viscous interaction. A portion of the large kinetic energy associated with flow at high Mach numbers transforms into internal energy in the fluid due to viscous effects. The increase in internal energy is realized as an increase in temperature. Since the pressure gradient normal to the flow within a boundary layer is approximately 0 for low to moderate hypersonic Mach numbers, the increase of temperature through the boundary layer coincides with a decrease in density. This causes the bottom of the boundary layer to expand, so that the boundary layer over the body grows thicker and can often merge with the shock wave near the body leading edge. High temperature flow. High temperatures due to a manifestation of viscous dissipation cause non-equilibrium chemical flow properties such as vibrational excitation and dissociation and ionization of molecules, resulting in convective and radiative heat flux. Classification of Mach regimes. Although subsonic and supersonic usually refer to speeds below and above the local speed of sound respectively, aerodynamicists often use these terms to refer to particular ranges of Mach values. This occurs because a transonic regime exists around m=1 where approximations of the Navier-Stokes equations used for subsonic design no longer apply, partly because the flow locally exceeds m=1 even when the freestream Mach number is below this value. The supersonic regime usually refers to the set of Mach numbers for which linearized theory may be used, for example, where the airflow is not chemically reacting and where heat transfer between air and vehicle may be reasonably neglected in calculations. Generally, NASA defines high hypersonic as any Mach number from 10 to 25, and re-entry speeds as anything greater than Mach 25. Among the spacecraft operating in these regimes are returning Soyuz and Dragon space capsules, the previously operated Space Shuttle, various reusable spacecraft in development such as SpaceX Starship and Rocket Lab Electron, as well as theoretical spaceplanes. In the following table, the regimes or ranges of Mach values are referenced instead of the usual meanings of subsonic and supersonic. Regime velocity, general airplane change, airplane to aircraft characteristics Mach, no miles per hour km/h, subsonic 0.8614, transonic 0.81.2614, 921, supersonic 1.25921, 3000, 836, hypersonic 510, 3000, 836, 7000, 673, high hypersonic 1025, 7000, 673, 19,000, 180, re-entry speeds 25, 19,000, 30. Similarity parameters. The categorization of airflow relies on a number of similarity parameters, which allow the simplification of a nearly infinite number of test cases into groups of similarity. For transonic and compressible flow, the Mach and Reynolds numbers alone allow good categorization of many flow cases. Hypersonic flows, however, require other similarity parameters. First, the analytic equations for the oblique shock angle become nearly independent of Mach number at high tilde 10 Mach numbers. Second, the formation of strong shocks around aerodynamic bodies means that the freestream Reynolds number is less useful as an estimate of the behavior of the boundary layer over a body, although it is still important. Finally, the increased temperature of hypersonic flow means that real gas effects become important. Research in hypersonics is therefore often called thermodynamics rather than aerodynamics. The introduction of real gas effects means that more variables are required to describe the full state of a gas. Whereas a stationary gas can be described by 3 variables: pressure, temperature, adiabatic index, and a moving gas by 4 flow velocity, a hot gas in chemical equilibrium also requires state equations for the chemical components of the gas, and a gas in non-equilibrium solves those state equations using time as an extra variable. This means that for non-equilibrium flow, something between 10 and 100 variables may be required to describe the state of the gas at any given time. Additionally, rarefied hypersonic flows, usually defined as those with an Knudsen number above 0.1, do not follow the Navier-Stokes equations. Hypersonic flows are typically categorized by their total energy, expressed as total enthalpy mj/kg, total pressure kPa/MPa, stagnation pressure kPa/MPa, stagnation temperature K, or flow velocity km/s. Wallace D. Hayes developed a similarity parameter similar to the Whitcomb area rule, which allowed similar configurations to be compared. Regimes. Hypersonic flow can be approximately separated into a number of regimes. The selection of these regimes is rough, due to the blurring of the boundaries where a particular effect can be found. Perfect gas. In this regime, the gas can be regarded as an ideal gas. Flow in this regime is still Mach number dependent. Simulations start to depend on the use of a constant temperature wall rather than the adiabatic wall typically used at lower speeds. The lower border of this region is around Mach 5, where ramjets become inefficient, and the upper border around Mach 10-12. 2 temperature ideal gas. This is a subset of the perfect gas regime, where the gas can be considered chemically perfect, but the rotational and vibrational temperatures of the gas must be considered separately, leading to 2 temperature models. See particularly the modeling of supersonic nozzles, where vibrational freezing becomes important. Dissociated gas. In this regime, diatomic or polyatomic gases, the gases found in most atmospheres, begin to dissociate as they come into contact with the Bohr shock generated by the body. Surface catalysis plays a role in the calculation of surface heating, meaning that the type of surface material also has an effect on the flow. The lower border of this regime is where any component of a gas mixture first begins to dissociate, and the stagnation point of a flow, which for nitrogen is around 2000 K. At the upper border of this regime, the effect of ionization starts to have an effect on the flow. Ionized gas. In this regime, the ionized electron population of the stagnated flow becomes significant, and the electrons must be modeled separately. Often the electron temperature is handled separately from the temperature of the remaining gas components. This region occurs for free stream flow velocities around 3-4 km/s. Gases in this region are modeled as non-radiating plasmas. Radiation-dominated regime. Above around 12 km/s, the heat transfer to a vehicle changes from being conductively dominated to radiatively dominated. The modeling of gases in this regime is split into 2 classes. 1. Optically thin, where the gas does not reabsorb radiation emitted from other parts of the gas. 2. Optically thick, where the radiation must be considered a separate source of energy. The modeling of optically thick gases is extremely difficult, since due to the calculation of the radiation at each point, the computation load theoretically expands exponentially as the number of points considered increases.